Hello and welcome to this Triple Chemistry C3 Revision Monkey Hangout. The aim of this hour is to try and cover as much as I can of the Triple Chemistry course, ready for your exam next week. So just to give you a quick overview first of all, this is only for people who take in the triple part of the chemistry. So if you're just doing additional, then this video is not appropriate for you. But if you've been taught C3, you will recognise the following content. A little bit on the periodic table, so early versus modern and the trends in reactivity, etc. Water, so soft and hard water, how you soften it, how you purify water. Titrations, including calculations and method for titrations. We're going to talk a little bit about energy, bond energies, hydrogen, calorimetry, organic chemistry, so your alcohols, carboxylic acids, esters, how you analyse substances and find out what they are, so testing for the positive ions and negative ions, and finally the Harper process, describing how we make ammonia and also how we can change the equilibrium. So first things first then, let's start off with the periodic table. Before the modern periodic table, there were several versions that were made by different scientists. This one here is by a chap called Newlands. His early periodic table was called the law of octaves because he put every eighth element with similar properties together. So if we count along here, hydrogen and fluorine, 1, 2, 3, 4, 5, 6, 7, 8. So they were grouped together. Unfortunately, there are problems with his periodic table in that you ended up with elements with totally different properties being grouped together in these groups. For example, you've got oxygen and iron here, a metal and a non-metal, totally different properties, groups together. The other table over here is Mendeleev's tables. Now his was a bit more advanced because he left gaps for undiscovered elements. So he predicted what the properties of such elements would look like, and he knew that they were just yet to be discovered yet, so he left them out, and then everything fitted a little bit nicer according to their properties. So we've still got groups and rows or periods in these two tables. Both of them in the early days were ordered in terms of atomic weight, which is different to what we see now. So these were ordered by atomic weight. Finally, the last thing that we need to remind ourselves of is the fact that it's called a periodic table because similar properties occur at regular intervals. I'll just get that down here. It's called a periodic table because similar properties, occur at regular intervals. So like regular intervals, like periodically. So similar properties occur at regular intervals. That's why it's called a periodic table. However, the table that we look at now doesn't look anything like Newlands or Mendeleev's. It is complete. There's no gaps in it like Mendeleev's. And you will see still we're grouping elements with similar properties together. The group numbers here are important. They tell you the number of electrons in the highest energy level. So the number of electrons in the outer shell or the highest energy level. You have over here group 1, there's a few groups that we need to know. These are the alkali metals. You've got the middle block here, which is your transition metals, which are all of these metallic elements just here. Group 7 you need to know is the halogens. When they form ions, they're called halide ions, but the elements themselves are called halogens, and the noble gases. So they might ask you a comparative question between the metals. The properties of alkali metals here in group 1, they have a low density. In fact, these top 3 here will float on water. You may well have seen your teacher have a trough of water where the metal is floating and fizzing around on top of that water. So these are less dense than water. They form white compounds that dissolve. So sodium carbonate, for example, a compound of sodium is a white compound, powdery substance. If you were to put that in water, it would dissolve to form a colourless solution. And these alkali metals react with water to produce a metal hydroxide and hydrogen. So they react quite vigorously. You might need to describe what you see in this reaction. So you will see a gas given off, you will see fizzing, really quite a common question, observe what you see. Gas coming off, fizzing. The size of the metal piece on top will diminish as it reacts and dissolves, and it will form a hydroxide and hydrogen. So let's take sodium, for example. If we react sodium from here with the water, we will be forming sodium hydroxide and hydrogen gas. This is an alkaline solution formed. So you may well have had a teacher put universal indicator in the water and see that that comes out a purple colour because that's an alkaline solution. Compare this then to the transition metals. Still metals, however, they have a higher melting point, higher density, few properties. They're stronger, they're harder, they're less reactive than the alkali metals as well. You've got things like copper in here, just here. You know that that's a strong, hard, unreactive metal. This bit's quite important. They form ions with different charges. What that means is because they're in the middle of group 2 and group 3, these transition metals have a bit of a special property in that they can form, for example, let's take iron. Iron can be Fe2+ as an ion or Fe3+ as an ion. So they have different charges that they can take the form of. They form coloured compounds as well. So unlike here, where white compounds are formed, transition metals will form colourful compounds. You might have seen some of those chemicals brought out by your teacher in greens and oranges and yellows. And these make useful catalysts as well. So for example, iron in the Harper process, a transition metal that just here, used in the Harper process as a catalyst, and you might need to use that as an example. But going back to the ordering then, the modern periodic table is not ordered by atomic weights. Instead, it's ordered by proton number. So this came as the discovery of protons and electrons and neutrons came about. And as soon as all those subatomic particles were discovered, it was reordered in terms of proton number as opposed to atomic weight. Final thing then is with these halogens here. We'll talk about reactivity in a minute, but you will need to know about displacement reactions between these halogens. Now we'll talk about why in a minute, but as you go up the top of the group, the halogens are more reactive compared with the bottom of the group. So we can use those in a displacement reaction. For example, if we had chlorine reacting with sodium bromide, the chlorine here would displace the bromine because chlorine is above bromine in the periodic table. It's more reactive, and you end up with bromine plus sodium chloride. Notice that the halogens are an ide when they're an ion. This is an ionic compound, sodium chloride, whereas as an element, they're ene, I-N-E. Okay, moving on then to talk about their reactivity. This bit is tends to come up more in the higher part of the course, especially describing why they are more reactive, but everybody needs to know that with the alkali metals, which are our group 1 metals, as you go down, they become more reactive, and they have a lower melting point, I'll just put that as MP, and boiling point, BP. So as you go down the group of the alkali metals, you get more reactive, lower melting point, and lower boiling point. This is the opposite with the halogens, which is group 7. As you go down the group of halogens from fluorine down to astatine, they are less reactive, and the opposite again, they have a higher melting point and a higher boiling point. So let's have a look at why. To turn into an ion, these alkali metals will want to lose an electron. So where they have one electron in its outer shell, they will want to lose that electron. If you remember, in the middle of the atom, you have a nucleus with protons and neutrons. So overall, the nucleus has a positive charge. So with lithium here, the electron is very close to the positive charge of the nucleus. Therefore, there is quite a strong force of attraction between the positively charged nucleus and the electron. So it quite easily holds it in place, and it's a little bit more difficult for that electron to leave, compared with a much larger atom where you'd have, again, the positive nucleus in the middle, the outer electron on the outside that you want to leave to form a positive ion. You can see in this case, the electron is much further away from the nucleus. So if you're asked to explain why reactivity increases as you go down the group of halogens, you want to be talking about the fact that it's easier to lose an electron, which I'll just put as an E with a dash above it, because the distance between the nucleus and the outer shell electron, make sure you say that the nucleus is positively charged as well, and the outer electron is greater. So therefore there is a weaker attraction force between the nucleus and the outer shell electron. Okay, so some of you may have heard about electron shielding as well. That's the idea that explaining basically that there's a weaker attraction, because if you've got lots of electrons in the middle as you're going around the shells, etc., that is going to be shielding this outer electron from the positive pull of that nucleus. The opposite then can be said for group 7, which is the halogens. They are in group 7, therefore they have 7 electrons on the outer shell, again a positive nucleus. They're going to want to gain an electron. So if you are a smaller atom, it is easier for you to gain an electron to get a complete outer shell, and the opposite way around, because it's got a smaller distance between the outer shell and the nucleus, so a stronger force of attraction, compared with when you've got a larger atom, 7 electrons on the outer shell, you want to gain one more. However, it's less reactive because it's much more difficult to gain that extra electron because it's further away from the nucleus and a weaker force of attraction. Moving on to water then. First of all, really important for human life is drinking water. It must have low levels of salts and microbes in it. So in order to do that, you need to do these following steps. You need to choose an appropriate source of water. Okay, so perhaps one that is free flowing rather than, you know, a river a static pond containing lots of solid matter and lots of microbes in it. So an important, and one that's not contaminated as well. You need to choose an appropriate source of the water. You then pass it through filter beds to remove any solids. And then finally, the water is sterilised with chlorine. Occasionally, in some areas of the UK, you'll have fluoride also added to the water. You need to be aware of the positive and negatives of that. And the positives being that it improves dental health and it's good for your teeth. The negatives are surrounding the idea of whether it is ethical or not to add fluoride. So the idea that the consumer, as the person drinking the water, has no choice. And there will maybe side effects or other risks of disease or things associated like that. So risks of possible diseases or side effects that the consumer doesn't have the choice about because it's automatically put into water. They can't choose whether they add fluoride or not. When it comes to children, obviously, really bad teeth is a good idea because everyone then gets treated with fluoride. So it's helping, especially the dental health of children. Now, you could use a process of distillation to get pure water. So that's when you put your dirty water in here. You will heat up the water until it evaporates. And then here in the condenser, it would cool down and condense into water. So you'd end up with all your solids and dirty parts here and pure water at the end. But the trouble is with this is, first of all, it costs a lot of money. And secondly, it costs a lot of energy. Okay, so that's not really a feasible solution to be getting our pure water by distillation. So this, although it may not be quite as good, is a more appropriate process to follow. When we do get the water into a house, a lot of us have these water filters. They contain carbon and also often silver, and they'll have some kind of ion exchange resin as well, which I'll talk about a little bit later on when we talk about ion exchange. But the carbon in there will generally improve the taste of the water by removing lots of the extra little bits of solid and matter that you don't want in there. Silver is really useful because that will help to kill any microbes as well. And the ion exchange resin will cause the water to go soft, so it will remove any of the ions in there that are causing it to go hard. Let's move on then now to hard and soft water. Soft water, in some areas of the UK, they just happen to have soft water, but it's all to do with the geography and the rock types that are around the area and where the water source comes from. So soft water easily forms a lather, which is permanent bubbles, with soap. And the opposite of that is hard water. If you live in a harder water area, it's more difficult to form a lather with soap. This actually reacts with soap to form scum. Okay, so scum is formed by hard water reacting with soap. They might ask you to name, I'll write that again, they might ask you to name scum as the product of a reaction with hard water and soap. So the thing is, with hard water areas, is more water is needed to form, more soap is needed to form a lather. So it's more expensive when you're doing your washing and things like that, because more soap is needed to form the bubbles that are going to clean your clothes. And the hard water then contains ions. You need to know the names of these ions. It's hard because it contains calcium and or magnesium ions. It all depends on the rocks that the water lands on in the water source. And as the water lands on these rocks, then these calcium and magnesium ions dissolve into the water. So needing more soap then is going to have a little bit of a negative effect because it's going to cost more money. If you're going to need to put more soap and more detergent into washing machines, then it's going to cause money. However, So it's going to cause an increase in amount of money that you're spending. However, it does have some benefits because calcium is good for your bones, a little bit like we talked about fluoride before being good for your teeth. Calcium is good for your bones and teeth also, and also it helps to reduce heart disease. There's two different types of hard water. There's permanent hard water, and there's also temporary hard water. With permanent hard water, it will remain hard even when you boil the water. So it will keep those calcium and magnesium ions in there. It will remain hard when boiled. However, with temporary water, you can remove the hardness, so it will go softer when boiled. So for foundation, you need to know those two differences, but for higher, you need to know in a little bit more detail. For higher, you need to know about the fact that temporary water contains hydrogen carbonate ions, which are HCO3-. This is the carbonate, hydrogen carbonate ions, and they decompose when heating. Okay, so that's what helps to remove the hardness, because when they decompose, they react with the calcium and magnesium ions that we said from before that are in hard water, and they form carbonates. So for example, calcium carbonate can be formed if the calcium ion reacts with the carbonate form part of this hydrogen carbonate, and this leads to scale. So you might have had a look at the bottom of your kettle before and seen lime scale. Well, that's just this calcium carbonate precipitate being produced because the temporary hard water is only temporary and is causing these calcium ions to be removed from the water. So if you have your heating elements in the bottom of the kettle, okay, it will look a little something like that. It will end up getting covered in lime scale, and that will reduce the efficiency and reduce the amount of energy transferred to the water. So it will take longer to boil your kettle because the energy transfer is reduced. Why have we got set up for a titration when we're talking about water? Well, you can tell whether a water is hard or soft by doing a titration. So you might need to describe this method. You would set up the titration equipment with a conical flask. And if you remember the name of this one, it's a burette. And in here, you could put your water, so it could be hard or soft. And then in this burette, if you add a soap solution, what you could do is slowly add the soap solution drop by drop, swirling the conical flask all the time. And then you could see how much soap solution was needed to form a lava. How much soap solution is needed to form a lava. Okay, so if we remind ourselves over here, soft water, you won't need much soap solution and the permanent bubbles will form on top of the water. However, with hard water, you'll need a lot more soap solution. You might then need to even compare permanent and temporary, because permanent hard water will remain hard when boiled. So even if you put boiled permanent hard water in there, you need a lot of soap solution for the bubbles to form and the lava to form on top. So you could compare a variety of different types of water using a titration. Water softening then. So because of the problem with lime scale, mainly, a lot of people and a lot of industries want to soften the water before using it. So you don't want that heating element or those inside a kettle or a washing machine or whatever, you don't want that covered in lime scale, reducing the efficiency of it. So you might want to soften the water. And to do that, essentially you're removing the ions that make it hard. So you want to remove those calcium ions and magnesium ions. And one way that you can do that is through an ion exchange column. So there's two ways. We'll talk about this one first of all. Ion exchange column. You don't need to know it in too much detail. You just need to know that in an ion exchange column there is ion exchange resin, and to that sticks either sodium or hydrogen ions. When you run the water through that ion exchange column, like through a water filter, for example, the ions that make the water hard, so the calcium and the magnesium ions, I've not put the charges on here, but they're 2+, 2+, and plus, they would simply exchange with the sodium. And that's what detail you need to talk about it in. You need to say that the calcium and magnesium ions in the water exchange with the sodium ions. So what you'll end up with is them swapping places, so that you have the magnesium ions and the calcium ions stuck on the resin. And I suppose a little disadvantage, you've still got metal ions in the water, because you end up with sodium ions here in the water and soft water coming out. The other way then that you can soften water is to use sodium carbonate. So you might see some adverts on television for water softeners like Calgon. When you add sodium carbonate, these react with the calcium and magnesium ions. So calcium and magnesium ions. Don't forget, these are the ones making it hard. So these are the ones that you want to remove from the water, and they will form precipitates, so solids. So for example, calcium carbonate or magnesium carbonate in a precipitation reaction. But the trouble with this one is it's not a continuous process like the ion, let me write that again, not a continuous process like the ion exchange column. It's a batch process instead. Okay, so each time you have to add this to, for example, your washing machine, or industrially, if they got big machines, they'd have to add this batch by batch. But an ion exchange column is a continuous process. And also, the precipitate would then have to be removed at some point because that will clog up the equipment. So it'll be again a form of scale clogging up the machines. So that would have to be removed and reused. They might ask you to compare two methods of softening water by adding sodium carbonate or the ion exchange column. So just have a little look into that as well. Harper process then. The Harper process is the process by which nitrogen from the air, you need to know where these come from, so from the air, and hydrogen, which is normally from natural gas, is turned into ammonia, which is this NH3 on the other side. Note that all of these are gases reacting together. This symbol here means that the reaction is reversible. A lot of people find describing how you make ammonia a little bit difficult, but actually it's quite an easy process. You have 3 parts hydrogen to 1 part nitrogen. So 3:1 hydrogen to nitrogen going into the top of the reactor. To help with the reaction, you have an iron catalyst, like we discussed when we were looking at the periodic table earlier, transition metal. And these 2 gases will react together to form ammonia inside the reaction vessel. Then what needs to happen is the reaction vessel needs to be cooled, and liquid ammonia comes out of the bottom. And the last little bit is then the hydrogen and nitrogen that haven't reacted go back and are recycled into the reaction vessel. And this is a closed system. So that means no products can enter or leave, or any other molecule, in fact, can enter or leave the reaction vessel when it is a closed system. And why that's important is because this process needs to reach an equilibrium. We'll talk about that in a minute, and we'll talk about these two numbers in a bit more detail as well. These are the conditions for the reaction that you need to know. The Harper process on an industrial scale takes place at 450 degrees Celsius and at 200 atmospheres of pressure. This next little bit is for the higher tier mainly, so if you do foundation, feel free to skip on to the next bit on energy. So equilibrium then happens in a closed system for a reversible reaction, and what happens is the forward and the backward reaction happen at the same rate. So the point that nitrogen and hydrogen are making ammonia, and ammonia is turning back into nitrogen and hydrogen at exactly the same rate. So there's no change in the amount of reactants and the amount of product. So we describe that as the relative amount of substances staying the same. First of all, I'm just going to introduce the words exothermic and endothermic that you should know from studying additional science. So exothermic, meaning giving out heat, and endothermic reactions take in heat from the surroundings. So if you try and remember which way round is endo-exothermic, well, have a look at this molecule here and think to yourself, it needs to be broken down into two products. So this reaction needs to take in heat, like a thermal decomposition reaction where you have one thing that takes in heat and breaks down into the two products. So this one here is the endothermic. And in a reversible reaction, the opposite direction is exothermic. So we said earlier that the conditions needed for the Harper process are 450 degrees C and 200 atmospheres of pressure. We're going to look at now why those conditions are used. First of all, we're going to talk about what happens when you increase the temperature of a reaction. If you increase the temperature, will we make more nitrogen and hydrogen, or will we make more ammonia? Well, if you increase the temperature, that's going to favour the endothermic reaction, because that's the one that takes in heat and breaks down. You need to think about it like that. So if you increase the temperature, you are going to increase the yield, which is how much product you get from the endothermic reaction, because that's the one that takes in heat. So if you're making it hotter, it can take in more heat and break down. And therefore, you're going to end up with less ammonia, because that's the part that's breaking down. Sorry, my pen's going off. So you're going to end up with less ammonia. However, if you were to decrease the temperature, the opposite would happen. If you were to decrease the temperature, you'd then be favouring the exothermic reaction, so you'd have more nitrogen and hydrogen reacting together and an increase in yield of ammonia. So as the industrial process happens, the whole point of you doing this reaction is to produce ammonia. So if we remember that in our minds, that actually the lower the temperature, the more ammonia you would produce. Looking at pressure then, pressure here is at 200 atmospheres. If you increase the pressure in a reaction, because we're talking about gases, we can talk about pressure. It favours the reaction that produces the least number of molecules. So favours, sorry, my pen's really not working very well. So it favours the reaction that produces the least number of molecules. Let's put least molecules down here. So in essence, if we look on this side of the reaction, you've got, if we really put it simply, one molecule of nitrogen reacting with 3 molecules of hydrogen to produce 2 molecules of ammonia. So with this statement, it says increased pressure favours the reaction that produces the least molecules. So this reaction here produces the least number of molecules. If you think about it, if you squash all these gases together, you're going to push these 4 closer together, making it easier to react, and it's going to favour this reaction. So if you do increase the pressure, that's going to end up in more ammonia. So increased pressure would lead to more ammonia being formed. However, let's go back to the conditions that we said we had. We got 450 degrees and 200 atmospheres of pressure. But we've just said that a lower temperature would produce more ammonia and a higher pressure would produce more ammonia. So why are we restricted to these temperatures? Well, it's a compromise that you'll need to know about. Yes, if you decrease this temperature, indeed you would produce more ammonia. However, the reaction is too slow. So for example, you might say, well, if I did it at 200 degrees C, I'm going to produce 50 grams of ammonia, whereas I did it at 450 degrees C, excuse me, and I'm only going to produce 25 grams of ammonia. So why would they pick this higher temperature? Well, at 200 degrees C, it could take you 2 hours, for example, to get that 50 grams, whereas at 450 degrees, it might only take you half an hour to get that 25 grams. So the important thing is, yes, you need to know that the lower temperature produces more yield, but it happens at 450 degrees because there is a compromise between the amount of yield you get and the time it takes. Remembering back to additional science that temperature increases the rate at which a reaction happens. Pressure then, why aren't we ramping this pressure up to 1,000 atmospheres? Well, the equipment is too expensive and too dangerous to increase the pressure anymore, and the technology isn't there really to have such extreme pressures for this reaction. So it's a compromise again. We would want a higher pressure, but it's going to cost too much and the reaction vessel becomes too dangerous. Moving on then to look at energy in fuels. This diagram here is really popular in the exam, talking about using an alcohol as a fuel or perhaps some kind of food source. So they could be burning some food in a container and heating up a certain mass of water. They often ask this question here: how could you improve the experiment? They want the idea that you could put a lid on the beaker or protect it with insulation either side, because you want all the heat to be transferred from the food or alcohol source to the water. So bear that one in mind. You might see the word calorimetry in the exam. This is basically this setup here, using food or fuel to calculate the energy transferred to the water, so you can work out how much energy per mole the food or alcohol can transfer. You will get calculation questions on these, and if you do, there are a couple of red herrings that you need to watch out for. You will get given the equation Q equals mc delta T. It's very similar to that physics equation in P1, where it's E equals m times c times m times c times theta for the specific heat capacity. Similar, energy transferred equals mass of the water times specific heat capacity of the water times by temperature change. They will give you the specific heat capacity. What you need to remember is this M stands for the mass of water and not the mass of alcohol burned. That's where people trip up in this question. So if I just quickly go through this question with you, it says in one experiment, the temperature of 50 grams of water increased from 22 to 38.4 degrees. Calculate the energy released by burning that mass of fuel. So ignore the mass of the fuel, that doesn't matter. We're wanting the energy transferred, and this mass is the mass of the water. So write out your working out. Q equals 4.2 times 50 multiplied by the temperature change, which is 16.4, and that will end up with 3,444 joules. I just want you to bear in mind the mark scheme to go with this. If you don't put any work in, you're at risk of not getting any marks, but look carefully where they will give you a mark. If you don't get the answer right, you can still get a mark for working out the temperature increase or for writing down that the mass of the water is 50 grams. Okay, so just bear that in mind. Don't just leave it blank. Still try and get a mark if you do get stuck by doing those couple of things. Energy diagrams now, then you might be asked to draw them or finish off a diagram. You need to recognise this as the energy diagram from an exothermic reaction and this for an endothermic reaction. You'll need to draw on there where the activation energy is. So you can see that one here. It's from the energy of the reactants up to the maximum energy that you see in the reaction. So if I was to draw that one on here, I could draw that either side really, but I'll just draw that here. Straight arrow up, unlike mine, and label that as the activation energy. You might be asked to draw the overall energy change. So here, for example, the energy of the reactants and the energy of the products, the overall energy change is the difference between the two. So this one here is the overall energy change, or delta H. And on this side, again, just the difference between the reactants and the products. You don't need to know delta H, but you might see it on there as the overall energy change. And finally, you might be asked to show the effect of a catalyst. So a catalyst provides a different pathway. You'll need to know this definition for C3, a different pathway with a lower activation energy, which I'm just going to write as AE, a different pathway with a lower activation energy. So if you're asked to draw the effect of a catalyst, you can just draw a dotted line here just to show that that is an alternative pathway with a lower activation energy. They will also say, this is a really common question, how do you know the reaction is endo or exothermic? And you quite simply need to just say what you see. So for the 2 marks, for exothermic, you're saying the energy of the products, which is here, is lower than the energy of the reactants. And for an opposite way round, endothermic, you're saying the energy of the products is higher than, the energy of the reactants. So simply just say what you see. Don't try and overcomplicate that kind of question. Quick little bit on hydrogen then, just a tiny sentence really in the spec for C3, but they might discuss hydrogen as a fuel. Hydrogen burns in air in a combustion reaction to produce water. So this type of reaction would be combustion when you're reacting with oxygen from the air. And the advantage of this, obviously, is there's no carbon dioxide as a product. Unlike other fuels that are producing carbon dioxide linking to global warming, this is simply producing water, so it's a clean fuel. You don't need to know how fuel cells work, but the other way is using hydrogen fuel cells, and they produce electricity, okay, to power vehicles. So there's two sort of advantages in technologies in using hydrogen in cars, either in a combustion engine, hydrogen and oxygen producing water, or there's something called a hydrogen fuel cell that produces electricity. So think about that word cell and link it to electricity and circuits to power, oh, I put power fuels, it should be power vehicles. Next bit then on energy is bond energies. So there's this in the box here, you really need to remember to fully understand this. So energy is released when bonds are made. Okay, that's quite conceptually quite difficult to understand, but energy is released when bonds are made. This is a little bit more easier to take. When to break bonds, you need to take energy in. So energy is taken in or absorbed when bonds are broken. So you might be asked to calculate the overall energy change for a reaction, or maybe even whether a reaction is endo or exothermic using bond energies. The first thing that you need to do is remember to balance the equation, although mostly they'll probably balance them for you. So this needs a 2 and a 3. This is the Harper Process reaction, or just the exothermic version of it, which has given us the clue away there, but exothermic in this direction. I'll give you a couple of examples of how to I'll give you this example of how to calculate bond energy, and then you can do one yourself. They give you this part of it, which makes everything a lot easier. They show you the bonds in the reaction, and then all you need to do is look carefully. That is the molecule N2. You don't need to double it up. That is N2. There's 2 of them. So you'd have a look at the bond energy table, which they'll also give you over here, and we'll say 944 added to, and then we need 3 lots of hydrogen, and that's the hydrogen bond. So 3 times 436. And on the other side of the equation, you've got 2 lots of NH3. But if you look carefully, you need to circle the bonds that involve NH, 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 and we need 2 lots of those. So we need 2 lots of 3 lots of NH bonds. So 3, 8, 6. So this 3 here shows that there's 3 bonds, and this 2 here is because it needs to be balanced in the equation. And if you calculate that, you'll get to the point where you have 2252 and 2316. Often these are 3 or 4 marks, and you'll definitely get most of the marks by getting to this stage just here. And then if you take away this, or what's on the left from what's on the right, you'll end up with your energy change. So you'll have, don't worry about the plus or minus, but plus 64 kilojoules per mole. And what that means is the reaction is exothermic. Because it is a plus, it's given out energy. So it's an exothermic reaction. But in the answer, they won't look at the plus or minus too much. So don't worry about taking it away the wrong way. So here's a question for you to do on bond energies. They've given you the balanced reaction up here. Notice that 3 to 3 just there. Circle all the bonds as you go. If you want to have a go at the question, I suggest you just pause the video, get a scrap piece of paper and try and work it out, and then come back and see if you got it correct. So how I recommend you do it is make sure that you circle all the bonds that you're working out. So if you look at this first molecule, you've got 1, 2, 3, 4, 5 CH bonds, which is this one here. So we start off by writing 5 times 413. We then got a carbon-carbon bond, which people miss out a lot of the time. So we add that to one carbon-carbon bond, which is 347. And, sorry, that should say 347. And we then add that to this carbon-oxygen bond, which is 358. And finally, add it to OH, which is 467. And that's just for that molecule, so it's not working out. And then on the left-hand side of the reaction, we need to add that to 3 lots of O double bond O, which is 495. Okay, and that will end up with, on the left-hand side, having bond energy, a total bond energies of 4722 kilojoules per mole. And then we do the right-hand side of the equation. So we've got two lots of C double bond O. So we've got two lots of C double bond O. Add that to two lots of OH. So this is where it gets confusing. 3 lots of 2 OH, which is 467. And that will end up on the right-hand side with the bond energies in total of 5988. So if you then write it out like this, 4722, 25998, and take away the 4722 from the 5988, you end up with an energy change of plus 1276 kilojoules per mole. So really well done if you got that correct. If you got to this point, you'd have got most of the marks correct. But I would really recommend in these larger molecules to circle all the bonds to make sure that you've got all of them. Because you'll still pick up some marks, you can see here, if you didn't get the right answer, you still get marks for working out the bond energies on either side. And look carefully here, you get a correct subtraction of any calculated energy value. So even if you get these two numbers wrong, you even get a mark for a simple subtraction, which is a really easy mark to get. Titrations then. You might be asked to draw a method for a titration. It could be in relation to soap and hardness of water, like we discussed before, or it can be in relation to finding out the concentration of an acid or an alkali. So this method here I'm using to find out the concentration of an acid, and to first of all, finding the concentration of an alkali, because I've put the acid in the flask at the bottom. So this method here is one that you'd need to know to write out a method question for a titration. So I've put measure a known volume of acid using a pipette and place in a conical flask. Lots of people don't realise that this pipette is the instrument used to measure out the acid before it is put in the flask, because people think pipettes are those little small things on the top of universal indicator bottles, for example. Okay, when pipettes, there's proper scientific equipment which will measure an exact volume for you. So just bear that in mind. You don't want to be writing about measuring cylinders or anything like that. Try and use the proper piece of equipment, which is a pipette. Then you need to add a few drops of indicator into your acid as well and place it on a white tile. You need a white tile because that will help you clearly see the colour change from the indicator. Here then, you've got your conical flask, your known volume of acid, and your white tile with your your indicator is in the flask. Now you don't often use universal indicator. You'll often use something with just one clear endpoint. So one clear colour change that's going to tell you that that is no longer an acid. So something like phenolphthalein or methyl orange. On top then you clamp a burette and you fill that with your alkali until the meniscus of your alkali is at the point that it says 0. You open the burette tap and add the alkali to the acid, drop by drop, swirling each time, and then stop when your end point is reached. So when you see that colour change on your indicator. You could equally do this titration the other way around with the acid in the burette and the alkali in the conical flask, depending on what you wanted to work out. And then using that volume of alkali that you've just worked out, you can then work out the concentration of the alkali. And that's one thing that you might need to do. This is for higher tier again, so if you are doing foundation, feel free to skip on to the next bit. But the next thing we're going to cover is titration calculations. So this is one example I'll go through with you, then there's one question afterwards for you to do. So this is higher tier. Once you've done a titration like we've just discussed, you might need to use that to work out the concentration. So here it says, a student carried out a titration to find the concentration of sulfuric acid. 25 centimeters cubed, this unit's important, of the sulfuric acid was neutralized by exactly 34 centimeters cubed of potassium hydroxide. The potassium hydroxide had a concentration of 2 moles per decimeter cubed, and the equation is given below. So this needs to be balanced, make sure that it is. They've already done that bit for you in this case. And we've been asked to calculate the concentration of the acid in moles per decimeters cubed. So that tells us that we need to change this to decimeters cubed by dividing by 1,000 to get our units correct. So I always recommend you doing these in a table. So write down your acid, alkali, and I'm just going to denote N for number of moles, C for concentration, V for volume on both sides. And there's a triangle if you need to remember it. Okay, oh, that should say V, number of moles, concentration, and volume. So for the acid, you just have to write down what information you've got and what you need to work out. So I always put a question mark in the bit that you need to work out. We've been asked to work out the concentration of acid, so I leave that as a question mark. The volume of acid we've been given as 25, but we need to divide it by 1,000. So I write that down straight away as 25 divided by 1,000. And we don't know yet about N. On the alkali, again, look at the information that you've been given. You're given a volume of 34. 34 divided by 1,000, because it's in the wrong unit, and a concentration of 2. Now, the only thing that we can work out is this N here. So if you can't remember the triangle, if you write the units down, it'll help you, because this is now decimeters cubed. The concentration is moles per decimeter cubed. So if we need to work out the number of moles of alkali, what we need to do is we need to multiply these two together, okay, to get rid of the decimeters cubed. So we do 2 multiplied by 0.034, and we get a number of moles as 0.068. This is the difficult bit right here. We've got 0.068 moles, and we need to calculate the ratio of alkali to acid. That's where you need to recognise that this is potassium hydroxide, the alkali. There's the equation, the balanced equation says that in this reaction, there are 2 moles of alkali for every 1 mole of acid. So we've got a ratio of 2 moles of alkali to 1 moles of acid. So we can use this ratio to help us calculate the number of moles of acid, because we need half the number of moles that are here. Because we've got double the number of alkali, we need half the number of moles. So we need to halve the 0.068 to give us 0.034. And we can use this information then to work out the concentration in moles per decimeters cubed. Again, use the units to help you. We need to do the moles divided by the decimeters cubed. So we need to do 0.034 divided by 0.025, and we end up with 1.36, which we then write down here. Our concentration of our acid is my pen's going wrong, sorry, 1.36. Okay, here's one for you to try then. Feel free to pause the video and then give this question a go, and then replay it again and see if you got it correct. So I always start out, whenever I see these calculations, by writing out the table. My pen will allow me. Acid, alkali, oh, we're going back, hang on. Acid, alkali, and our NCV. We write down what we've got. So it says calculate the concentration of ammonia. So that's our alkali, that's what we need to work out. We've been given the volume of ammonia, so 25 divided by 1,000. We've been given the volume of our acid, so 20 divided by 1,000, because this is centimeters cubed, we need it decimeters cubed. And we've given a concentration in 0.25 moles per decimeters cubed. So the one thing that we can work out is the number of moles of acid by multiplying these two together. So we end up with 0.005. To get the number of moles of alkali, we look at our ratio. This is a ratio of 1 to 1, making sure this is balanced first of all. So we've got a ratio of 1 alkali to 1 acid. So therefore there's the same number of moles on this side, 0.05. And we can use that to work out the concentration. So if we remember our triangle, N C times V. Or if we look at the units, that's moles, that's decimeters cubed, and the units for concentration are moles per decimeter cubed. That reminds us that we need to do the number in moles divided by the number in decimeters cubed. So 0.005 divided by 0.025 gives a concentration of 2. So our concentration of our ammonia is 2 moles per decimeter cubed. Final couple of units then. We're going to now talk about, try and get rid of that writing. Okay, bear with me. Okay, we're back working again. Sorry about that. We're now going to talk about, oh, I don't know why that was back again. Okay, let's try this. Sorry about that. We're now going to talk about identifying substances. So when you've got an ionic substance like sodium chloride or magnesium sulfate or lithium nitrate, you've got something that's positive bonded to something that's negative. So we're going to look at, if you just randomly found some powdered substance, how could you work out what that was? How could you find out whether that was sodium chloride or magnesium sulfate or lithium nitrate? Well, there's a couple of tests you need to do. You need to test for the positive ion and you need to test for the negative ion. And then once you know those two things, you're able then to name the compound. So let's start off then by looking for the tests for positive ions. First of all, you can use flame tests. So these will help us identify the following 5 that you need to know: lithium, sodium, potassium, calcium, and barium. One way to remember it is lithium is crimson. So if I do a little rhyme for you, which I'll try and write with my pen, little criminals. Okay, I don't think that's really not going to work. I'll just read it out for you. So if you remember, if you've got a pen handy, little criminals, nasty youths, kick little, cats round, back gardens. So just a little phrase for you to try and remember them. So you get the LI here for the little, CR for the criminal. So lithium crimson, little criminals, sodium yellow, nasty youths, K for potassium, kick, little for lilac, cats, round, back, gardens. Okay, so it's just facts that you need to remember. Put them down on a post-it note or somewhere, something for you to try and remember. What you do is you'd have an inoculating loop, so just a small piece of metal wire. You'd pass that through a Bunsen flame to sterilize it, make sure there's no other pieces of metal on there. You would then dip it into your solution containing your metal or into your powder, and you would then put that back into your Bunsen flame. And the flame would go the colour of the metal, so crimson, yellow, lilac, red, and green. One thing that's really common as a question is why it's not possible to identify the metals if there's more than one metal in the compound, and that's the idea that one metal flame will mask the other. So if you had, it's the masking that's really important. So if you had lithium and sodium together, if you put those 2 in the flame at the same time, well, you'd have crimson and yellow, and you might not see that yellow in the flame because the crimson is overpowering it and masking it. Other tests that you can do then, if the flame test isn't available for you, or if there's other positive ions that you want to test for because the metal ions were inconclusive, well, you need to add sodium hydroxide to your solution. So sodium hydroxide has the symbol NaOH, and you need to add sodium hydroxide solution to your sample, and you'll end up with different precipitates. So you'll end up with green. That is if you have the positive ion, which is iron 2. Iron 2 is because you've got different charges on the ions, which I discussed earlier, Fe2+. You could have an orange, which they tend to describe in the exam more as a brown colour, so just for you to be aware of that. And that would be iron 3, which is Fe3+. You could have a blue precipitate formed, precipitate just being the solid that's formed, and that is indicative of copper. And finally, you could have a white substance formed. Now that could either be aluminium, or it could be calcium or magnesium. So it will be a little bit inconclusive if you have a white precipitate. And one thing you can do is find out whether it's aluminium or not. These two, you could do a flame test and this would be red. But if you add excess sodium hydroxide, so that's add even more, this aluminium will disappear. So this precipitate will break down again and disappear if excess, which means lots more until no more reacts, sodium hydroxide is added. The way I remember that is if you say aluminium in the American accent, in the way that they say aluminium, they say aluminum, and that to me sounds a little bit like a spell in Harry Potter or something like that. If you say aluminum, it will disappear. So that will help you remember, or maybe not, the white precipitate that disappears is aluminum or aluminium. A couple more tests then that we need to know about. Testing for halides, which are the ions from the halogens form. If you remember back, we were talking about group 7 and the halogens. They form halide ions. So the test for halides is to add silver nitrate solution and dilute nitric acid. So the nitrate solution and the nitric, that should say, acid go together. And what you end up with, apologies again for my pen, what you end up with is several different precipitates formed, which we'll discuss in just a second. Test for sulfates then. If something is, for example, magnesium sulfate or iron sulfate, it'll have SO4 on the end of the compound, and you need to add dilute hydrochloric acid, and you also need to add barium chloride, and we'll talk about what precipitates that makes in just a minute. And finally, for testing for a carbonate, maybe you've got sodium carbonate or magnesium carbonate, you need to add dilute acid. So let's start off with the bottom one actually, because let's think about it. If we add acid to a carbonate, what gas are we going to make? We're going to make CO2. So if you have a carbonate and you add acid, CO2 will get given off, which turns lime water cloudy. Testing for halides then at the top, there's 3 that you can make. Because you've added silver nitrate to your halide, you end up with a precipitate, which is a solid, that will either be silver chloride, if you've got something chloride, like magnesium chloride or iron chloride. You could make silver bromide as your precipitate, or you can make silver iodide. So adding this silver nitrate will allow us to check whether in our compound we have a chloride, a bromide, or an iodide, because the silver chloride precipitate will be white, the silver bromide precipitate will be cream, and the silver iodide precipitate would be yellow. One way to remember those colours is that it gets darker as you go down the periodic table. So if you look at the halogens in group 7, chloride, bromide, iodide, the colours of their precipitates get darker as you go down. Test for sulfates then, because you're adding barium chloride, you're going to end up with barium sulfate being made if you have a sulfate compound, and this barium sulfate is going to give you a white precipitate. So if you add dilute hydrochloric acid and barium chloride to your compound, then if a white precipitate forms, you know you've got yourselves a sulfate. So these ones are really difficult to remember. It might just be a case of writing them down 2 or 3 times and then brain dumping them when it comes to the exam. Final topic you'll be pleased to hear is all about organic chemistry. So when we mean organic, we talk about things with carbon in it, so alcohols, carboxylic acids, and esters. Alcohols, first of all, then, they have an OH functional group. You need to recognise this on a molecule of an alcohol. All of these alcohols, methanol, ethanol, propanol, form a homologous series. So homo meaning the same. So they are very similar molecules and they only differ by one small parameter. So homologous meaning they all have the same functional group and they just change by a few atoms in the molecule. But apart from that, all the structure is the same. So how we write the formula of alcohols, we tend to write them by looking at the displayed formula here. So if you look, CH3, CH2OH. We always have the functional group on the end to show us clearly straight away that it's an alcohol, and we just read it as this. There's CH3, CH2OH. You'll need to have to draw methanol as well. So if you remember, monkeys eat peanut butter. That's the order of the number of carbons. So methanol has 1 carbon, ethanol has 2 carbons, propanol has 3 carbons, and butanol would have 4, and so on. But you only need to know the 3. So methanol then, 1 carbon, 1 has the functional group attached to it, which is the OH. You can either draw them together or with a bond in between them. And then you just need to fill in the other carbons. Ethanol is the one I've drawn up here. You can see that it's got 2 carbons, and that's how you know it's ethanol. And finally, propanol has 3 carbons. The end carbon has the functional group. And then you just need to complete all single bonds of hydrogen around that. So how would we write it? Well, for propanol, if you look here, we've got CH3, so we'd write that as CH3, CH2, CH2, OH, showing us that it's an alcohol. Methanol then, we'd write as CH3, OH. So you need to be able to draw and write the formula for those 3 alcohols. Next then is a little bit of detail on the alcohols. First of all, that they dissolve in water to form a neutral solution, which is obviously different to our carboxylic acids, which we'll talk about in a minute. They burn in air. Obviously, that links to them being a useful fuel, and it's the oxygen in the air that they burn with in the combustion reaction. They're useful solvents, so lots of compounds will dissolve in them. That's why they're useful cleaners, because if you can't clean up something with using water as your solvent, if, for example, the dirt on the table wasn't dissolving in the water, you might want to use an alcohol, because the dirt then might dissolve into the alcohol. And you need to be aware that ethanol is the main alcohol in alcoholic drinks. The final thing that you need to be aware of is that they react with sodium to produce hydrogen. So one random reaction you need to know about. Let's take ethanol for an example. Ethanol will react with sodium to produce something called sodium ethoxide. I'd be very surprised if they asked you about sodium ethoxide, but we need to remember that that's producing hydrogen gas. Moving on then to carboxylic acids. Again, they are all part of a homologous series, so they've got the same functional group as each other. It's different to an alcohol though. This is the functional group, and we write that as COOH. Remember, every carbon's got 4 bonds, so this is a double bond to an O, single bond to the OH, and then a single bond here. If we work out what acid this is, well, it's got the same prefixes as before, the meth, the eth, the prop. So 2 carbons would make it ethanoic acid. And we write it in a similar way. We group things here, so CH3 followed by the functional group at the end, COOH. So if we were to draw the compound for methanoic acid, we'd have 1 carbon, because it's meth. We'd have the functional group, and then we'd have our final bond here needs to go to a hydrogen. Propanoic acid, 3 carbons. Start with the functional group at the end so that you know that you've got that one sorted, and then fill in the rest with single bonds, single covalent bonds to hydrogens. Again, if we're naming these, this one, we'd call it, probably the most difficult one, but HCOOH. And this one down here, we'd call it CH3, CH2, COOH. So if you see a molecule like this, you need to be able to name it by counting the carbons. You'd count the carbons, know there are 3, so it must be prop, and recognise the functional group and know it must be a carboxylic acid. So how do we get here then? How do we get from alcohols to carboxylic acids? Well, basically these need to oxidize and be reacted with oxygen or have oxygen added to them. And there's 2 ways that you can oxidize the alcohol. You can either use a chemical, so use an oxidizing agent. Sorry, that's not going to write. I'll just have to say it, unfortunately. But the alcohol needs to be oxidized. It needs to have oxygen added to turn into a carboxylic acid. And there's 2 ways that you could do that, either by an oxidizing agent or by microbial action. For example, if you leave a bottle of wine open, you've got your alcohol, your ethanol in the wine, and the microbes in the air can cause that to turn into a carboxylic acid by oxidizing, adding oxygen to the alcohol, and then you end up with a vinegary taste, which is your carboxylic acid being produced. A couple of things on carboxylic acids then. First one's pretty obvious. Unlike alcohols that form a neutral solution when they dissolve in water, these are acids. They perform just like all other acids in the fact they produce acidic solutions when they dissolve in water. And all of the reactions that the carboxylic acids do are very similar to your main 3 lab acids that you use, your hydrochloric, your sulfuric, and your nitric. They, for example, react with carbonates to produce carbon dioxide. One important thing for the higher tier, though, is to understand why carboxylic acids form what we call weak acids. Weak acids mean that if you had a 1 molar ethanoic acid compared to a 1 molar nitric acid, which is not a carboxylic acid, this would form a weaker acid. So if you were to have a look at its pH, this one would have a higher pH, so a weaker acid, than the nitric acid over here, even though they have the same concentration. And the reason being is the following. The whole thing that makes an acid is the presence of hydrogen ions. So when these carboxylic acids here dissolve in water, they don't ionize completely. They don't completely split into hydrogen ions like this. Okay, so you would expect this part of the molecule to separate from the hydrogen ions, this making it acidic. However, they don't completely ionize. Really common question, so make sure you've got this in your heads ready for the exam, that they form weak acids because they don't ionize completely, and that will mean that there were lower numbers of hydrogen ions. Final page then, you'll be pleased to hear, is on esters, and this brings together our alcohols and carboxylic acids, because to get to an ester you need to react an alcohol with a carboxylic acid. For example, here we've got ethanol. We react that with ethanoic acid, so this is our alcohol, this is our carboxylic acid, and we end up with this molecule here, which is our ester. This is the only name of ester that you need to know, so you need to be able to complete that word equation. For ethanol plus ethanoic acid would make ethyl ethanoate. However, any given molecule of an ester you need to be able to recognize. Now, you know that's not carboxylic acid because it doesn't end in COOH. You know it's not an alcohol because it doesn't end in OH. But this is the functional group for an ester. It's in the middle or somewhere in the middle of the molecule. So we say that's COO rather than COOH. And that's how we distinguish our esters. Now, the thing with these ester molecules that we can make, they're useful in flavorings and in perfumes. Okay, because they have two very special properties. They're volatile. That means they turn into a gas really easily. So maybe you've made an ester in the lab and suddenly it will smell really nice because it turns into a gas really easily. And also, just like I said, they smell nice. They're fragrant. Okay, they make nice smelling molecules. So they're used in the perfume industry and for flavorings as well. So that sums up all the content that you need to know for Triple Chemistry C3. I wish you the best of luck in the exam, and hopefully you found this video useful for you. If you have any further questions, feel free to comment below.